Hello physics class. Okay, so today we're going to do circular motion and gravity, right? We've already discussed gravity a bit in the previous chapter, but this time, right, gravity, but this time we're going to talk about how planets orbit the sun, right? We orbit the sun, it takes 1 year. If you say, hey, I'm 19 years old, well, what you're saying is that since you've been alive, the Earth has gone around the sun 19 times, right? That's what you're really saying. Okay, so let's get into it. And we're going to analyze gravity in more detail. Actually talk about Newton's law of gravitation and good stuff like that. And more math, of course, but it's not too bad. Okay, let me get set up here and bear with me, we're all used to this. Okay, that looks pretty good. All right, does the circular motion of the moon around the Earth, these PowerPoints are funny, have anything in common with the circular motion on Earth? Oh man. I'm intrigued now. Let's see. We'll find out. Okay, so a ball is whirled on the end of a string with a constant speed when the string breaks. Which path will the ball take? This is actually a really important concept. A lot of people would think, okay, maybe a lot of people would pick 4. They would think, well, so the ball was sort of, if you're here and you're twirling, you have a ball on a string and you're twirling it over your head or something, it's going around and the string breaks. So a lot of people might think, hey, well, it's going to kind of go on a circular path or fly out. No, it's not going to do that. It's not going to do that. Okay, and then, so you have to think about this. The string broke right at an instant. So it broke right at an instant, right? So it's going around. So what you have is at that instant, the ball has a direction, right? Right? And it also has a velocity. So the answer is path 3, right? So right at the instant when the string broke, the ball was going in this direction, right? If it's going around this way. So it's just going to continue in a straight line. It's not going to curve, because to curve, there would have to be some kind of a force on it to curve. If it had some kind of fins on it or something with, if it's a baseball, you can do a curve ball, but that's because it's spinning, and then the baseball has the little ridges where the threads go in, so the air affects it. But here we're not talking about that. Here it's just going to go straight. It's going to continue in the direction that it had at the instant when the string broke, right? This is Newton's law. An object continues in motion unless there's a force that acts upon it, right? So it's just going to continue. It's not going to go this way. It's not going to go this way. There's nothing here to change its direction. The string breaks in whatever direction it was going in, and the direction it was going in was this direction, right? And then, right? Okay. If the spring breaks, the ball flies off in a straight line path in the direction it was traveling at the instant the string broke. There is no other, unless there's another force acting on it, it's just going to continue in that direction. Yeah, Newton's first law, right? So circular motion, and we call it centripetal motion, right? You've probably heard that term. We're going to use centripetal motion more often. And the string was providing a centripetal force. Force. Remember, and the reason is because the direction was changing. Remember, we talked about that. Even though this velocity would have been the same, but the direction is changing, right? Okay? So centripetal acceleration is the rate of change in velocity of an object that is associated with the change in direction. So even though, you know, from instant to instant, the speed is the same, the velocity, right? It has a definite direction, Remember, velocity is a vector, so it's a speed with direction. Well, it definitely has a definite direction. And the change in direction is towards the center, right? You can tell that. So with vector addition, right, if you wanted to see what the change was between V1 and V2, well, it's the difference between the vectors. But instantaneously, right, and there's a tension on a string, it's always directed right back at the center of the circle, okay? Centripetal acceleration is always perpendicular to the velocity, and it always points towards the center of the curve. Well, that makes sense. Just think about that's wherever the string is. The string is always going back to the center, right? So that's the direction that it doesn't go back there, but that's where the acceleration points towards the center. It makes sense because the string is there. The string is what has the tension. It's not going to be anywhere else. The only place there's tension is in a string. And it's directly perpendicular, right? At this point, it's going this way. At a 90-degree angle, it points right back at the center. Okay, it takes a little practice to think about that, but that's what we're doing here. And yay, a math equation. I know you're all happy about that. Okay, so centripetal acceleration is equal to the velocity squared divided by r. That's not too bad. And of course, the units are going to work out, right? Are you going to practice that? Well, yeah, you will. Okay, centripetal acceleration is the rate of change in velocity of an object that is associated with a change in direction. Remember, velocity is a vector, so it has a direction. So if you change the direction, okay, so it's, I know in our common language, if you change velocity, you're thinking, well, you know, the actual speed. No, but in physics, if the direction changes, that's a change in velocity, right? Speed is where you don't have direction, okay? Centripetal acceleration is always perpendicular. We showed that in the previous example. The acceleration always points towards the center of the curve. That's where the tension is in a string. There is no other pointing or anything anywhere else. That's all that there is. Okay, changes direction, not speed, right? Remember, speed is not the vector. Velocity is a vector, so direction matters. Okay, force refers to any force or combination of forces that produces a centripetal acceleration. And there's our favorite equation of this chapter. Okay, well, this is good, right? So force equals mass times acceleration. We already know about that equation. So the good news is here we're sort of just, well, we're just using it again, except that when we're talking about centripetal force, right, we'll put a little subscript there. When the subscripts are there, we're talking about a centripetal, right, a circular motion, okay? Makes a difference. You don't want to get them mixed up with if you're just going in a straight line. Now, so if you're here, if you're holding this string and you got a ball, you know, a little ball or a marble or something, and you're spinning it. Again, remember how when we did projectile motion, it was kind of like two equations or two separate problems. There was the gravitational force pulled it down, and then you just had the velocity going that way. Well, so we're used to that. We've already worked with that sort of concept, so it's happening again. Gravity is still pulling on this ball, so you have the weight component going down. The ball still weighs the same, right? But then you have a tension, right? There's a tension on the string, which is because of the centripetal acceleration and the weight, right? But it has two components. There's the horizontal component, and there's the vertical component, which is equal to the weight. Okay? Okay, and here they're talking about, so we showed the example of a ball and a string, but it's similar. If you're in a car and you're going around a curve, well, so it's the same kind of motion. You're an object and you're going in a circle, but what's preventing you from just going there? Well, it's the friction forces of the tires. The tires, right? They when they make tires, they think about that. They make tires so it sticks to the road, right? A bit. No, it doesn't stick. I mean, you can go, but it sticks if you try to go sideways, right? The tread patterns and such. So it's the force of friction instead of the string. So that's where the tension is, okay? So a static force is if you just go around the curve and you're fine. If you're one of these, sideshow people, right? You see those in the Bay Area where they're skidding around and stuff. Well, now there's a kinetic force where yeah, you're sliding, but there's still friction holding you. You're not flying off and into the sidewalk or something like that, hopefully, right? So they're balancing it. Well, that's a kinetic force of friction where you're still using friction, but you're sliding a little bit. Okay. And here's a good example, right? So here's this car and it's going around a curve, but it's not flying off into the embankment, right? It's holding the tires are what's giving you that tension. There's not a string attached to the car as if it was a ball. Now, if you bank the curve, this is why when you're getting off the freeway and stuff, and our California freeway system, well, they bank a lot of the roads when they know there's a turn, because now you're not just relying on the tires, right? Part of the components are actually pushing into the road, right? So that's why they bank, and they do that on purpose, of course. And they know physics. The people who do that, the traffic engineers, they understand physics, right? Yeah, this is a Ferris wheel, so all right, planetary motion. Yeah, geo, you see the word geo a lot. Geology, geography, right? Geo means Earth. It means Earth. So when you have a geocentric, right? The ancients, they thought that Earth was, or some of the ancients thought that Earth was static and that the sun and everything went around the Earth. Well, it looks that way, right? Well, now we know that's not the case. We are actually, the sun is at the center of our solar system, and our meager little planet goes around the sun just like all the other planets, right? We're special, but we're special just like everyone else, right? Just like every other planet. We're special as every other planet, okay? And we're not going to talk about the astronomy. Take an astronomy class, right? It's important. It's important. Okay, well, we'll talk about this. So Copernicus, he came up with a heliocentric. Helio means the sun. So he came up with a heliocentric view, which is what we know is correct now. The sun is at the center of our solar system, and all the planets go around the sun. Okay, and later on, a guy by the name of Tycho Brahe, he calculated a lot of data, very accurate data on the positions of the planets, and then. Right, and he had these big instruments. They didn't have telescopes yet. There was no telescopes, but they just measured the position of the planets in the sky using these big sextant type things where they measured the angles very accurately, and they wrote it all down. And all those records still exist, right? Science, take data, go by your data, right? And then Kepler worked for Tycho, and then he analyzed all that data, and he came up, and they found out that Earth, it's not a circular orbit around the sun. It's actually, this is exaggerated, but it's actually an ellipse. We have a slightly elliptical orbit around the sun, and the sun is at one focus, right? And that's just geometry. If you have a circle, there's a focus in the center. If you have an ellipse, right? If you stretch the circle, you have two foci, right? And so the sun is at one focus, and we go around, and all the planets, they're all slightly elliptical, right? Yeah, all of the planets that orbit the sun, they're elliptical orbits. they're not as, this is exaggerated, you know, they're only slightly elliptical, but they are nonetheless elliptical. So, okay, and then, so that was Kepler's first law. His second law was that planets sweep out equal areas in equal intervals of time. Well, so if Earth is going around the sun in an elliptical orbit, right? Well, when it's closer to the sun, it goes faster. It does that. It has to balance the gravity because it's closer to the sun. When you're closer to a body, the gravity is more intense. As you go far away, it's weaker. Well, we know that if you're on the moon, you feel the moon's gravity, right? The astronauts, they didn't feel Earth's gravity anymore, but when you're on Earth, you feel the Earth's gravity. As you get far, far away, it gets weaker and weaker, right? We don't worry about the stars' gravity. Stars are really far away. But if we were near those stars, we would worry about that gravity quite a bit. So this is just saying say, you know, it takes 1 year for Earth to go around the sun. So say these were approximately, instead of 25 days, 30 days, so a month. So way out here in a month, you would only move this much. But when you're closer to the sun in a month, you would move this much because you're going faster to balance the gravity. If you didn't go faster, you would get sucked into the sun and we would get all burnt up, right? Then the third law is that, you know, Kepler was really good at mathematics. So the period of an orbit, let's go to the next one. Yeah. The period of an orbit, so that's just the time it takes to go around the sun once. If you square that number, okay, it's equivalent to the radius cubed. So he was able to determine that, and that's good to know. If you know how long it takes one of the planets to go around the sun, you can calculate that its average distance from the sun. Not too shabby, huh? Okay, Newton's law of universal gravitation. Yeah, Isaac Newton, right? He lived centuries ago. He was the guy when there was the plague. He went on his farm. He did social distancing on his farm, right? And once the plague was over, then he went back to England and he had his job at the university and all that stuff, right? Genius who invented a lot, so. And this is a thought experiment that Newton came up with. It's called Newton's cannonball. I have an entirely separate video. This is important. So I made you're going to watch your own a video just on that topic. So we're just going to skip ahead here and you'll watch that other video for that. Okay, but what Newton, one of the other things that Newton discovered, there's an equation that determines the force of gravity between two objects. You know, anything that has mass has gravity. You know, this pen, there's a gravitational attraction from this pen to this computer screen. There's you know, my hands, there's a gravitational attraction. It's very weak, right? You only feel it when there's big things like you know, the force of gravity. So this pen clearly is being attracted to Earth, right? We'll do this. I'll let go, but Earth is big compared to us, so the gravity is strong. The more mass you have, the more gravity you have, right? It's a warping of space-time, right? Albert Einstein discovered that. We're not going to get into that. That's another physics class altogether. But Newton discovered that say if you have mass 1 and mass 2, and say mass 1 is the sun, mass 2 is us on Earth, and then, so he discovered if you multiply mass 1 by mass 2 and divide it by the radius of the orbit, so the distance between them, and you square it, right? And then you multiply it by a number g. Well, g, don't be scared by this equation, right? It's just, all that does is it makes the numbers match what we now know from experimentation, but it just well, let me go to the next one. Yeah, the universal gravitational constant g. So it's a proportionality. It makes the proportion of the mass 1 times mass 2 divided by r squared. It's a proportionality constant that allows you to mathematically calculate accurately the force of attraction between two bodies, okay? And the way we figure that out these days is you can measure it. Oh, it didn't give the number. Okay, well the number is in the book. Maybe it's going to give the number back. Let me go back up. Hang on, bear with me. I'm looking for the number. I didn't see where it gave that. All right, well it's in the book. And we talk about it in the laboratory. So let's go here. Okay, you noticed here, so the force, right? It's inversely proportional to the square of the distance. So how does that work? Let's try and visualize that. So if you have a mass here, say if this is Earth, right? We're on Earth, and we know that the moon orbits Earth. We have satellites that orbit Earth. The International Space Station is up there. Elon Musk is launching all kinds of things. Other companies are, right? Well, the farther you go from Earth, the gravity gets weaker because basically it's spreading out, right? It's a geometrical thing. So if you have this distance from the Earth, and say you were here in your spaceship, right? The gravity would be sort of concentrated in this area. But if you double that distance, well, the force of gravity doesn't go down by 2, it's the square. So it goes down by 4 because it's just spread out. It's like if Earth was a balloon, right? And you were blowing it. Well, at this distance, it would just be bigger, but it has the same mass. So the force of gravity is based on mass, right? So it decreases by a factor, by a square, the inverse square of the distance. If you went 3, it would decrease by 9 because that would be 1/3 squared. So here you can see each one of these squares is the same size as this square. So here the force of gravity is decreased 9-fold. So this is just a illustration that can help you visualize the math a bit. Okay, now if you have two big bodies, so if you're up in space and you have, this is Earth and this is Mars, right? The gravitational force of attraction acts along a line. So what you do is it's as though all the mass is at the center, right? When you're doing the calculations, it's as though all the mass is at the center. So you would measure from the center of one mass to the center of the other, and the direction is going to be from one center to the other, right? Along that direction. Okay? So that's good. It makes, you don't have to worry that, like for instance, Saturn is quite big, but it's very fluffy. It's like if you had an average chunk of Saturn, the planet Saturn, and threw it in water, it would float, right? Saturn is, but as us, we're very dense, right? If you take a rock, pick up a rock and throw it in the water, it's going to sink, right? Earth is much more dense, right? So it's not the size, it's the density. Oop. Let me go back here. Okay. All right. I think, yeah, so we know that the moon orbits the Earth. I think that's it. All right, folks, that's it.